This video is the fourth installment in a series showing how to approach calculating the pH at various points in a weak acid strong base titration. We previously calculated the pH of the given acetic acid solution prior to addition of any base, and after 10 and 25 milliliters of the sodium hydroxide solution was added. In this video, we will calculate the pH of the solution after 50 milliliters of the sodium hydroxide solution has been added. Calculating the pH of any titration requires you to initially treat the situation as a stoichiometry problem, which means that we first need to determine how many moles of hydroxide ion was added to the solution. To do this, we will multiply the concentration of sodium hydroxide by the volume of sodium hydroxide added. For 50 milliliters of a 0.10 molar solution, that comes out to being 0.005 moles of hydroxide ion. Since we can assume all reactions involving strong bases go to completion, we can determine that after the reaction is complete, the solution will contain 0 moles of acetic acid, 0 moles of hydroxide ion, and 0.005 moles of acetate ion. We have now reached the equivalence point of the titration, where the number of moles of base added is equal to the initial amount of acid that was present. Since the volume of the solution is changed, we can't directly use the initial concentration of acetic acid to serve as the concentration of acetate ion present. We will need to calculate the new concentration by dividing the number of moles of acetate ion by the new volume, in this case 0.1 liters. We can now treat our problem as being about 0.05 molar acetate ion solution. For the next step, we will write out the equilibrium reaction for the deprotonation of water by acetate ion. This is because the strongest base currently present in the solution is the acetate ion, and the strongest acid is water. We can now set up our ice table for the concentrations of acetate ion, acetic acid, and hydroxide ion. The initial concentration of acetate ion will be 0.05 molar, and the concentrations of acetic acid and hydroxide ion will be 0. Based on the equilibrium equation, for every mole of acetate ion that is consumed, we should produce a mole of acetic acid and a mole of hydroxide ion. To signify this stoichiometry in the ice table, we will state that the concentration of acetate ion will decrease by x, and the concentration of both the acetic acid and the hydronium ion will increase by x. Now we can combine the values we have for the initial concentrations and the expected changes to give us the equations for our equilibrium concentrations. Since we are now working with the deprotonation reaction of water by acetate ion, we will have to set up our equilibrium expression using Kb. We know that the product between the Ka of an acid and the Kb of its conjugate base is equal to Kw, the autoionization constant of pure water. We can quickly calculate the value of Kb for acetate ion, which is 5.6 times 10 to the negative 10. Now, we can set up our equilibrium expressions where Kb is equal to the concentration of hydroxide ion times the concentration of acetic acid over the concentration of acetate ion. Plugging in the equilibrium values from the ice table gives us the mathematical expression x squared over 0.050 minus x equals 5.6 times 10 to the negative 10. We can now solve for x by doing some algebraic manipulations of the equation and using the quadratic equation, which will give us a value of x is equal to 5.3 times 10 to the negative 6 molar, which is then also the concentration of the hydroxide ion. We can now solve for the pH by setting up the expression 14 plus log of the hydronium ion concentration to get a pH of 8.72.